Mastering Algorithm Design. Strategies for solving complex programming challenges in today's fast-paced technological landscape. Programming algorithms serve as the backbone of efficient problem-solving across industries ranging from artificial intelligence to blockchain development. Understanding how to design and implement effective algorithms isn't merely a skill, it's a necessity for engineers navigating modern software architecture. This deep dive explores both foundational principles and cutting-edge methodologies in algorithm design, offering practical insights for developers seeking to optimize performance metrics and tackle real-world computational challenges with confidence. The fundamentals of algorithmic thinking at its core. Algorithmic thinking involves decomposing complex tasks into logical sequences of operations that computers can execute efficiently. This approach requires identifying patterns, recognizing constraints, and formulating solutions that balance correctness with resource efficiency. Effective algorithm designers understand that every decision impacts runtime performance and memory usage. By mastering basic constructs like loops, conditionals, and recursion, programmers gain the ability to craft elegant solutions even for seemingly impossible problems. Consider the classic Tower of Hanoi puzzle. What initially appears as a simple game reveals profound lessons about recursive decomposition when analyzed through an algorithmic lens. Such exercises sharpen analytical skills essential for tackling complex systems engineering projects. Sorting algorithms. From bubble sort to quantum computing, bubble sort may seem quaint compared to modern implementations, but studying classical algorithms provides critical insight into comparative performance metrics. These early methods laid the groundwork for more sophisticated approaches now dominating high-performance computing environments. QuickSelect, a variant of Quicksort, demonstrates how partitioning strategies can dramatically impact selection operation efficiencies. When implemented correctly, this method achieves linear average case complexity, making it ideal for median-finding applications. N log n, time complexity. Algorithms like merge-sort maintain predictable performance characteristics regardless of input order spacetime trade-offs. In-place sorts conserve memory but often sacrifice speed advantages of external storage variance stability considerations. Maintaining original element ordering becomes crucial in multi-key sorting scenarios. Quantum sorting algorithms represent emerging frontiers in computational theory. While still theoretical, research suggests potential exponential speedups for certain classes of problems, promising transformative implications for cryptography and data science domains. Searching techniques beyond binary division. Binary search remains a cornerstone technique, but contemporary approaches incorporate probabilistic models and heuristics to handle incomplete information. These adaptive methods prove invaluable in machine learning feature selection processes. Spatial indexing structures like KD trees enable efficient nearest neighbor searches in multidimensional spaces, a capability critical for geospatial analytics platforms handling terabytes of location-based data daily. Probabilistic data structures such as Bloom filters offer fascinating alternatives when exact answers aren't required. Their space-efficient nature makes them indispensable in network routers managing vast amounts of packet metadata traffic. Data structures integration. Enabling algorithmic innovation. Choosing the right data structure often determines whether an algorithm succeeds or fails. Hash tables provide constant time lookups, while balanced trees guarantee logarithmic access times, an essential consideration for database query optimization. Fibonacci heaps exemplify specialized structures optimized for particular algorithmic needs. Their amortized O(1) decrease key operations make them ideal companions for Dijkstra's shortest path algorithm implementations. Doubly linked lists facilitate bidirectional traversal capabilities, proving particularly useful in text editors requiring frequent insertion/deletion operations during document manipulation. Memory-mapped files combine file system persistence with direct memory access, enabling innovative approaches to big data processing frameworks that challenge traditional RAM limitations. Dynamic programming. Optimizing through subproblem reuse. Dynamic programming transforms seemingly intractable problems into manageable components by leveraging overlapping subproblems and optimal substructure properties. This paradigm shift enables efficient solutions where brute force would otherwise fail. The knapsack problem illustrates DP's power beautifully. The same framework applies to portfolio optimization in finance and resource allocation in cloud computing infrastructure management. Memoization serves as a powerful tool for storing intermediate results, preventing redundant calculations while maintaining clean code structures. However, excessive memoization risks converting algorithms back into brute force approaches. Caching strategies vary depending on application context. Least recently used, LRU, policies work well for temporal locality patterns, whereas Bilaty's algorithm represents theoretically optimal page replacement decisions though rarely practically implementable due to its non-causal nature. Greedy algorithms, short-term gains versus long-term vision. While greedy approaches often yield suboptimal results, their simplicity makes them attractive choices for constraint satisfaction problems where near-optimal solutions suffice. Scheduling algorithms frequently employ greedy paradigms to maximize throughput under strict deadlines. Huffman coding stands as a landmark achievement demonstrating greedy methodology's effectiveness. Its prefix-free property ensures lossless compression while achieving asymptotically optimal entropy bounds. Activity selection problems showcase how local optima don't always align with global solutions. Nevertheless, these algorithms remain popular in real-time systems prioritizing immediate availability over perfect outcomes. Approximation guarantees become crucial when evaluating greedy strategies. Knowing the percentage deviation from optimal helps engineers make informed trade-off decisions based on system requirements. Divide and conquer. Breaking down computational barriers, the divide and conquer paradigm excels at transforming large-scale problems into smaller, independently solvable components. Matrix multiplication exemplifies this strategy, reducing O(n) superscript 3 complexity through clever block decomposition techniques. Fast Fourier transform (FFT) algorithms epitomize the elegance of divide and conquer approaches. Their O(n) log n complexity revolutionized signal processing and became fundamental to modern encryption protocols. Strasson's matrix multiplication algorithm showcases how mathematical insights can lead to breakthroughs in algorithmic efficiency. Though theoretically superior, practical implementation considerations sometimes favor conventional approaches. Versions of this principle appear in parallel computing architectures, where workload distribution across processors follows similar hierarchical division patterns to achieve scalable performance gains. Graph algorithms, navigating interconnected systems from social media networks to transportation infrastructures, graph algorithms help us understand and optimize interconnected systems. Depth-first search, DFS, and breadth-first search, BFS, provide foundational exploration mechanisms with distinct discovery priorities. Dijkstra's algorithm maintains its relevance despite newer developments by consistently delivering shortest paths in graphs with non-negative weights. Variance incorporating priority queues enhance its adaptability across diverse applications. Minimum spanning tree algorithms demonstrate how connectivity optimization influences everything from circuit design to telecommunications. Network planning. Prim's and Kruskal's approaches differ primarily in their incremental construction strategies. PageRank, originally developed for web search rankings, reveals how eigenvector centrality measures can quantify node significance in massive directed graphs containing billions of connections. Optimization problems. Finding the needle in the haystack combinatorial optimization problems define the boundaries of tractable computation. Traveling salesman problem, TSP. Variations continue challenging researchers with their NP-hard complexity class status despite decades of study. Linear programming relaxation offers approximate solutions by transforming integer constraints into continuous variables. This technique proves particularly useful in logistics and supply chain management optimizations. Genetic algorithms mimic biological evolution to explore solution spaces through mutation, crossover, and selection operators. These heuristic methods excel at finding good enough solutions within reasonable timeframes. Simulated annealing introduces temperature parameters to control exploration-exploitation balance, making it especially effective for problems exhibiting rough landscapes with numerous local minima. Concurrency and parallelism. Scaling algorithm performance as hardware continues evolving toward many core architectures. Algorithm redesign becomes imperative to harness available compute resources effectively. Task parallelism allows independent computations to proceed concurrently, maximizing processor utilization. Lock-free algorithms represent a significant advancement in concurrent programming, eliminating bottlenecks caused by mutual exclusion mechanisms. However, designing such algorithms requires deep understanding of memory consistency models. Data flow execution models decouple computation from data movement, enabling dynamic scheduling that adapts to changing workloads. This flexibility becomes crucial in distributed systems handling unpredictable input volumes. Parallel suffix arrays demonstrate how domain-specific knowledge can unlock new avenues for algorithm acceleration, combining string matching techniques with parallel processing capabilities for genome sequence analysis. Evaluating algorithm efficiency. More than just Big O notation provides essential theoretical foundations, but real-world performance depends on numerous additional factors including cache behavior and branch prediction accuracy. Benchmarks should consider these practical dimensions alongside asymptotic analyses. Andel's law reminds us that sequential portions limit overall speed-up potential, emphasizing the importance of optimizing hotspots rather than prematurely micro-optimizing less impactful areas. Gilbert's law introduces a novel perspective on algorithm evaluation, considering both computational cost and communication overhead in distributed systems contexts. This dual-metric framework guides better architectural decisions. Profiling tools offer empirical validation of theoretical predictions, revealing discrepancies between expected and observed performance. Regular benchmarking helps identify regression opportunities before they become production issues. Ethical implications in algorithm design. Modern algorithm design carries ethical responsibilities beyond mere functionality. Bias embedded in training data can manifest as discriminatory outputs in facial recognition systems, necessitating proactive fairness-aware algorithm development. Transparency requirements drive demand for explainable AI models, compelling algorithm designers to balance predictive power with interpretability constraints. This tension presents ongoing challenges in healthcare diagnostics and autonomous vehicle decision-making. Differential privacy techniques inject controlled noise into datasets to protect individual identities, showcasing how algorithmic innovations can address societal concerns related to data protection and surveillance. Algorithmic accountability demands robust auditing mechanisms to verify compliance with legal standards while maintaining operational efficacy. These considerations reshape how we approach algorithm deployment in critical infrastructure sectors. Future directions in algorithm research. Neural Turing machines represent exciting frontier research merging neural networks with symbolic computation capabilities. These hybrid models suggest potential breakthroughs in program synthesis and automated theorem proving. Quantum supremacy experiments raise intriguing questions about algorithmic possibilities enabled by quantum superposition and entanglement effects. Shor's algorithm already threatens current cryptographic standards, prompting urgent research into post-quantum cryptography. Automated algorithm generation through genetic programming shows promise for creating novel solutions without human intervention. This area intersects closely with reinforcement learning techniques in robotics and control systems. Federated learning architectures distribute computation across devices, protecting user privacy while still enabling collective model improvement. This approach redefines how we think about decentralized algorithm deployment. Conclusion. Programming algorithms form the bedrock of modern technology, influencing everything from mobile app responsiveness to national security infrastructure. As demonstrated through this exploration, mastery requires both theoretical depth and practical ingenuity. To thrive in this rapidly evolving field, aspiring engineers should prioritize hands-on experimentation with various algorithm families while staying attuned to emerging research trends shaping future innovation directions.